October 1944. Rechlin Airfield, Mecklenburg, northern Germany. Cold wind blew across the runways, carrying the smell of gunpowder from battles 200 miles away. Allied bombers often passed overhead in large groups, but tonight the sky was quiet. Inside Hangar 12, a group of Opel Blitz trucks stopped under bright lamps. The guards stood straight as Oberfeldwebel Karl Voss, chief mechanic of the Rechlin testing center, walked forward. His breath showed in the cold air as he ordered, "Uncover it." Under the cover was the damaged fuselage of a Supermarine Spitfire Mark 14, code PL3780, shot down by a Focke-Wulf 190A8 near Calais. Its wings were bent, and its engine area was badly damaged. From the wreck, one part stood out, a Rolls-Royce Merlin Mark 130 engine, a V12 power unit covered in oil and residue. Voss knelt and touched the metal. This was not a normal engine test. This was the British engine that had helped the Allies gain air superiority. Tonight, they wanted to discover its secrets. Rechlin Airfield was not just a repair center. It was the Luftwaffe's main testing and research base, where captured Allied planes were studied to learn their technology. Since 1939, German engineers had tested parts from Hawker Hurricanes and Bristol Blenheims to improve their own aircraft. Voss's team of 10 mechanics had already rebuilt a P-51B Mustang earlier that year, but could not reproduce its special wing design because of aluminum shortages. The Merlin engine, however, was something different. Reports from pilots said that Spitfires were climbing higher and faster than German planes. "It's the boost," said Lieutenant Fritz Harlan, the team's engine expert. "2 stages with cooling between them." Voss replied coldly, "We don't guess, we test." The hangar filled with the sound of tools and machines. They began removing panels and lifting the fuselage. The smell of oil and metal filled the air. The Merlin engine weighed around 1,650 pounds, but was compact for its size. It had a 27-liter capacity, 24 valves, and sodium-cooled exhausts. Voss noted the details carefully. Compression ratio 8.5 to 1. Earlier, Merlin engines had single-stage superchargers that lost power above 18,000 feet. The newer German DB600-312 engines used direct fuel injection, but still could not match this version. Rumors said the Mark 130 Merlin could produce around 2,000 horsepower, giving the Spitfire a top speed of 448 miles per hour at high altitude. By mid-morning, the mechanics opened the supercharger housing. Inside, Harlan found something new: 2 impellers, not 1. Between them sat an intercooler, a device that cooled the compressed air. The first impeller ran at 6.4 to 1, the second at 9.3 to 1, switching automatically at about 10,000 feet. There were also water methanol injection ports to prevent engine knocking, allowing very high boost pressure with 150-octane fuel. Voss recognized the design. "This is Hooker's work," he said, naming the British engineer Stanley Hooker, who had developed the system in 1942. The 2-stage supercharger had already helped Spitfire Mark 9 aircraft outperform the Focke-Wulf 190 over Dieppe in 1942. Tests showed it kept about 80% efficiency compared to only 65% for the German Jumo 213 engine. That meant it could hold 1,700 horsepower at high altitudes where other engines lost power. Next, they mounted the engine on a test stand built from steel beams. Harlan connected it to an electric motor. The hangar echoed as they started the pumps. They used the limited 87-octane synthetic fuel they had left. Harlan pressed the starter, and the engine came to life with a deep growl. Flames came from the exhaust as it warmed up. The supercharger made a high-pitched whine, and the floor vibrated. The gauges showed strong performance: manifold pressure plus 18 inches, oil at 110 degrees Celsius. "It runs smooth," said Harlan, impressed. "No surge, no vibration." When Voss increased the throttle, the sound became a roar that shook the hangar roof. The test readings showed 1,400 horsepower at sea level. The Germans were shocked. This engine was far beyond what they expected. At noon, Voss shut down the engine. The air smelled of burnt oil and metal. Harlan quickly drew diagrams of the impellers and intercooler. "We can copy it," he said confidently. But Voss knew the truth. Germany lacked the materials, and their factories were being bombed. Their fuel quality was also too low for this kind of boost. Still, he ordered another test for the evening. "Prepare the high-altitude simulation. We'll push it to the limit." The men got back to work as the daylight faded. Outside, they could hear distant anti-aircraft guns, but inside, their attention stayed on the Merlin engine, which still seemed alive, a machine that represented both the enemy's power and their own desperation to catch up. Evening came to the hangar as the October sky outside Hangar 12 turned dark blue. Searchlights moved slowly across the horizon. The electric fences around Rechlin hummed, mixing with the steady sound of generators starting the altitude chamber. A large steel cylinder, 30 feet long, with heavy vacuum pumps that made the floor shake under Voss's boots. The Merlin engine, placed again on the test stand, stood under bright floodlights. Its supercharger housing had been closed, the intake system connected to a test air scoop, and the exhaust pipes fitted to a water brake dynamometer. Harlan checked the throttle controls, his hands stiff from the cold air that smelled of oil and warm metal. "Set the vacuum to 20,000 feet, Voss ordered. The pumps began to run faster, their noise rising sharply. The pressure gauge dropped as the air inside the chamber thinned to match the high-altitude conditions where Spitfire Mark 14s usually operated. Outside, a Ju-88 aircraft landed on the runway, but inside the hangar, everyone focused on the test. The goal was clear: to understand how this British engine worked so well at high altitude. The crew stood around the setup. Voss was at the controls, Harlan watched the boost gauge, and the technicians observed their instruments. The Merlin's starter motor turned, activating the magnetos. Fuel vapor filled the intake, and the V12 engine started roughly before running smoothly. Exhaust gases came out through short pipes, creating a visible heat wave, and the smell of half-burned aviation fuel made to copy British 130-octane petrol. "Open the throttle," Voss said. The carburetor slides moved, and manifold pressure rose to plus 12 inches of mercury. The crankshaft reached 2,000 revolutions per minute. The pistons hit their rhythm, and the supercharger's first impeller, with a 6.4-to-1 ratio, began to spin. The deep hum filled the hangar like distant thunder. At simulated sea level, the dynamometer showed 1,450 horsepower and 3,000 foot-pounds of torque. The Merlin ran very smoothly, unlike the rougher BMW 800s. "Stable," Harlan reported, writing the readings on a clipboard wet with condensation. Pressure continued to fall, now equal to 15,000 feet. Frost began forming on the chamber walls. The automatic switch activated with a small click, engaging the high gear coupling. Gears connected with a faint noise, and the second stage impeller reached overdrive at a 9.3-to-1 ratio. The pitch of the sound rose quickly, the frame vibrating under the strain. Boost pressure stayed high, plus 20 inches, then 22. The intercooler cooled the compressed air, keeping temperatures near 120 degrees Fahrenheit, while similar German engines, such as the Jumo 213, often overheated. Water methanol injectors opened at 80% throttle, sending a fine mist into the intake and lowering the temperature by about 60 degrees below ambient, which prevented knocking. Power increased 1,600 horsepower, and then more, as the crankshaft reached 3,000 revolutions per minute. "It's maintaining," Voss said quietly. Unlike the DB600-512 engines that lost power above 12,000 feet, this engine kept its strength. At simulated 20,000 feet, the Merlin produced 1,710 horsepower, with air density similar to 5,000 feet at sea level. Its impeller efficiency reached 83%, far higher than its German counterparts. Harlan wiped sweat from his forehead and checked the gauges. Exhaust temperature stayed at 1,000 degrees Fahrenheit, cylinder heads at 280, and there were no signs of overheating. The sound filled the entire space. The high-pitched whine of the supercharger and the deep growl of the V12 together created an almost painful vibration. The smell of fuel and oil became heavy, and ozone crackled from the pressure seals. Voss briefly pushed the throttle to war emergency power, raising boost pressure to 25 pounds per square inch, using simulated 150-octane fuel. The Merlin responded with a strong surge, shaking the stand as the dynamometer reached 2,000 horsepower. Blue flames appeared from the exhaust pipes as methanol burned. The whole setup seemed alive, straining against its mounts.
2,000 even, Harlan shouted. Holding! No knock! No surge! The team watched as the gauges stayed stable for 30 seconds, then 40. The engine remained cool and balanced. In their tests with Jumo 213s, engines often seized after 20 seconds at that pressure, but the Merlin kept running normally. When Voss finally reduced power, the engines slowed smoothly, its cooling system working perfectly.
When he shut off the ignition, the sudden silence felt heavy. The engine slowed to a stop, and the chamber slowly filled with normal air again, bringing a cold, metallic smell. Harlan leaned against a post, exhausted, while others stood in silence. Voss walked around the test area, remembering the readings. Climb rate about 2,500 feet per minute for a loaded Spitfire Mark 14, service ceiling 44,000 feet, top speed 448 miles per hour. This was the secret, Stanley Hooker's two-stage supercharger design from 1942. By stacking impellers and cooling the air between stages, he had increased air density without losing efficiency. Earlier engines like the Mark V from 1941 had only one stage, and their impeller blades were set at 15 degrees to improve flow. But this new two-stage design changed everything. It gave the Royal Air Force control of high-altitude air combat. Voss touched the Merlin's cooling fins as the metal cooled. "We can match the DB603 at low altitude," he said quietly. "But up there, nothing. Their mosquitoes fly above our night fighters. P-51Ds escort bombers over the Ruhr without fear." The men discussed options. "Reverse the gears," suggested Becker, one of the mechanics. "Fit it to a Fokker-Wulf." Harlan shook his head. "The gearing is too precise. Our machines can't make those tolerances." They all knew fuel was another problem. British high-octane petrol resisted knocking. German C3 fuel could not handle high boost. Voss lit his pipe. The smoke mixed with the smell of burned oil. Reports came from the Eastern Front. Spitfire. Mark 18s attacking Sturmovix at high altitude, their engines running perfectly in extreme cold. Rechlin's mission was to copy and improve, not to admire, but the difference was too wide. British factories at Derby and Crewe built about 200 Merlins each month, 168,000 total by the end of the war, while German engine lines at Augsburg suffered from poor materials and limited production. "Berlin wants prototypes," Voss said, exhaling smoke. "By spring, a DB613 with intercooler and two-speed supercharger." Yet he doubted they could reach it. The Ardennes offensive was coming, and Allied aircraft already dominated the skies. Night settled fully. The team covered the Merlin with a tarp, the fabric making a soft sound in the still air. Voss stayed behind, writing notes and sketches, impeller shapes, boost charts, heat control diagrams. Harlan came over quietly. "Oberfeldwebel, if we can't match it?" Voss looked at him, serious. "Then we study it. Every part, every ratio, until we learn or fail trying." The hangar doors closed with a heavy sound, sealing the engine inside. But the echo of its 2,000 horsepower stayed with them. The test had not given them victory, it had shown them how far behind they were. The skies now belonged to engines like this one, a machine whose clever use of air and pressure had changed the war. Inside the silent chamber, the Merlin rested, its secret still safe, waiting for the next test. At dawn on October 2nd, 1944, pale light spread across Rechlin's frozen airfield. Frost covered the ground where Me-116s taxied in uneven lines, their Jumo 213 engines coughing from low fuel. Inside Hangar 12, the air was still and heavy with the smell of old exhaust and metal. Voss had not slept. His small bed in the officer's hut stayed untouched. On the table beside it lay open notebooks, cigarette butts, and cold coffee cups. Harlan slept in a chair near a pile of blueprints, snoring softly. The rest of the crew was already moving, their boots scraping on the floor as they ate black bread and margarine under the weak yellow lamps. The Merlin engine stood in the center of the hangar, repaired but still open in some parts. Its surface showed small marks from the last test, proof that it had reached 2,000 horsepower for a short time. Voss crushed his cigarette under his boot and said quietly, "The metals team from Dessau arrives at 8 o'clock. We check the alloys first, then we talk about replication." His voice sounded tired, without the excitement he had the day before. Outside, a crew worked on a Focke-Wulf 190D, its Jumo engine coughing blue smoke as it started. Those aircraft could still fight during the day, but they struggled to climb high. The team from Dessau arrived soon after in a Kübelwagen covered with bullet holes. 3 engineers stepped out, carrying full briefcases. Their leader, Dr. Ernst Klemm, was thin, with small glasses that fogged up as he stepped inside. They walked straight to the Merlin like doctors at a patient's bedside. The hangar slowly grew warmer as heaters buzzed. Klemm touched the crankshaft pulley carefully. "Nickel, chromium, molybdenum steel," he said, scraping a bit off to test it. "It's heat-treated to Rockwell C58, with a fatigue limit of 120,000 pounds per square inch. Our 4100 series bends at half that." The engineers worked quickly. They used cameras and scopes to check the cylinders, which had a thin chrome layer resistant to corrosion. They noted that the valve seats were made of stellite alloy, designed to handle pressures up to 300 pounds without damage. Harlan compared their notes to his sketches. "The exhaust ports are shaped to make the airflow smoother, about 12% less back pressure than our DB engines," he said. Klemm nodded and examined the impeller blades. "Radial tips shaped perfectly, shockwave control at Mach 0.8. We've been chasing this design since Peenemünde in 41. By 10 o'clock, the engineers had filled the old conference table with charts and metal samples. Voss spread out the Supercharger schematic. It showed 2 connected stages, a small one feeding air to a larger one, increasing pressure at high altitudes. "Gearbox tolerances," Klemm said, pointing at the gears. 30-degree angle, backlash 0.005 millimeters. Our machines cannot cut that smoothly. The room grew tense. "Fuel system," Harlan added. "SU carburetors. No floats, so they work under -G. Ours flood during dives." Klemm wrote quickly. "They use water methanol mix to prevent detonation, up to 20%. That's how they reach +25 boost. But the main problem was the materials. The British used high-temperature alloys like Nimonic 75 and Inconel for valves and turbine parts. These metals stayed strong at 850 degrees Celsius. German alloys, low on nickel, softened at 750. "We can only get close," Clem admitted. "We can upgrade the DB 613 with one intercooler and a 7-to-1 ratio, maybe 20% more power at high altitude." Voss leaned forward. "And how long?" 6 months for each prototype," Clem said quietly. "Factories in Alash are running all day, but only 40% of parts pass inspection. Allied bombers slow everything." Then the phone rang. Bad news from the front. German fighters near the Scheldt had lost 8 Focke-Wulf 190s to 12 Spitfires from Manston. The British fighters climbed higher, their Merlin engines strong at 32,000 feet. The Doras fell behind at 26, their engines gasping. Voss could imagine it clearly, the Spitfire's wings slicing through thin air, their engines roaring with perfect balance. The Merlin's power came not only from strength, but from precision, automatic mixture control, spark adjustment, and careful engineering. Clem showed photos from a captured de Havilland Mosquito. Its twin Merlin 66 engines produced 1,750 horsepower each. "Can we use this design for the TAR 152? Voss asked. Clem laughed softly. "Impossible. The Heinkel's airframe isn't made for inlines. A redesign would take 6 months, and our synthetic fuels can't handle plus 25 boost. The British use 150 octane. We can't make it." By afternoon, the engineers moved to the testing lab, a small glass room filled with measuring equipment and machines that hummed softly. Inside were coordinate measuring arms, metal analyzers, and pressure testers. The air smelled of oil and metal dust. They studied the Merlin's steel samples under microscopes. The results were clear. The British steel had only 0.04% carbon and almost no sulfur. It was extremely pure. German factories could not reach that level anymore. Most electric furnaces had been destroyed by Allied bombings in the Ruhr area. Harlan checked the torque tester connected to the Merlin's accessory drive. As the machine rotated, the magnetos delivered 250 volts without any sign of failure. Hydraulic pumps produced 3,000 pounds per square inch, enough to move landing gear smoothly. "It's the balance," Harlan said quietly. "Every system fits together perfectly. Our DB engines perform well in dives, but they fail in cold, thin air. This one still works at high altitude." Clem nodded as his analyzer beeped. "Look here, trace amounts of vanadium in the bearing shells. It makes them hard, but not brittle. We've lost access to that element because of the blockades." The room grew warm from the heaters. The smell changed from machine oil to graphite dust as they prepared to test a copy of the Merlin's Supercharger impeller. The Rechlin workshop had built it overnight, trying to match the British design. The test began. The impeller spun faster and faster until it reached Mach 0.9, then shattered suddenly. The blades broke apart like glass, flying across the room. The German engineers stepped back in silence. The real Merlin impeller, however, had survived 11,000 revolutions per minute without breaking. Its metal quality and precision balance made all the difference. As the day ended, the engineers realized how far behind they were. The Merlin's strength did not come from a single invention, but from hundreds of small improvements. Careful design, perfect materials, and consistent production. When the evening siren sounded, Voss gathered everyone near the hangar doors. The Merlin engine had been packed in a wooden crate, covered with a tarp, and marked for transport to Oberammergau, where secret research projects were stored. 2 SS guards with MP40s stood watch beside it. Clem packed his notes into a metal case. "I'll report to General Milch by the end of the week," he said. "We'll propose a hybrid design, Add a two-stage supercharger to the Jumo 213E for high-altitude fighters. That should give us about 1,600 horsepower. It's not perfect, but it's something. Voss frowned at the word adequate. Adequate for what? The Allied P-51 Mustangs, each with a Merlin engine capable of escorting bombers across Europe, the Mosquitoes that flew high and fast with twin Merlins. The numbers spoke for themselves. 168,000 Merlin engines built in Britain, used in over 40,000 aircraft. By comparison, Germany had produced about 80,000 V12 engines, split among too many types and experimental versions. Harlan stayed near the crate, resting his hand on it. "We took it apart," he said softly, "but we never really understood it." Voss placed a hand on his shoulder. "No one does," he said quietly. "Not until the plans are gone." The Kübelwagen engine started with a rough growl. Its two red taillights faded into the distance as it carried the Dessau engineers away through the cold night. Rechlin slowly returned to its normal work. Mechanics warmed up the engines of Arado trainers, and anti-aircraft crews practiced under the yellow lights of the perimeter towers. Voss stood near the hangar door, holding an unlit pipe between his teeth. The evening wind was cold and dry. He looked at the packed Merlin engine, now sealed and ready for transport. Somewhere in the south, it would be locked inside an underground storage area, guarded and studied again. But deep down, Voss knew that no copy would ever match the real thing. The Merlin's secrets, its balance, its precision, its careful engineering, could not be fully copied. Even the stolen data would only lead to small improvements. These efforts would feed into projects like the DB-613's failed two-stage supercharger and the TAR-152's later design compromises. They would all end as short notes in the long list of failed wartime experiments. By May of 1945, when the war finally ended, the skies over Germany were almost empty. Messerschmitts and Focke-Wulfs lay destroyed on abandoned airfields. Their pilots, once proud aces, parachuted into Allied lines where they were captured and traded bits of technical information for food. At Rechlin, the feeling of loss had started months earlier. Not when the bombs fell, but when the engineers realized what they were facing. The British had achieved something Germany could not match, a perfect combination of design, resources, and production. The real strength of the Merlin engine was not just its power, it came from the teamwork between engineers like Stanley Hooker, who improved the airflow systems, and the thousands of factory workers in Britain who built the engines under strict quality control. Even during the hardest times, Rolls-Royce managed to produce engines with the same precision every time. Germany, on the other hand, was running out of resources. Nickel, chromium, and high-octane fuel were in short supply. Many factories had been destroyed or forced to move underground. The result was engines that looked powerful on paper but failed at high altitudes or after long missions. As Voss turned away from the hangar, the metal doors closed behind him with a heavy clang. The sound echoed across the airfield. The Merlin's success was not just about technology, it was about planning, organization, and time. Britain had all three. Germany, trapped by its own ambition, had none left. The war would continue for several more months, but for Voss and his mechanics, the real defeat had already happened. It wasn't on the battlefield or in the sky. It happened in the silence of the hangar, when a captured engine proved that their best work could not reach it. That engine, the Merlin, had not only powered aircraft, it had powered a victory built on intelligence, patience, and unity.